Hi guys, our last exam explanation review day seemed like a big success in terms of people engaging and looking at questions and trying to get some really good practice for the AP exam. What I'm decided to do today is take all of your suggestions and try to put lots of options here for people who want and need it. So this first page, I have compiled all of or many of the things that I think could be good things that you would have to explain for each of our topics. So we're going to hit some of those highlights together. I have also found one more question for each topic in a separate video. It's going to be linked right up here. I am going to go through these key points, kind of talk through them, maybe write a little bit, but mostly talk through my thought process. Some people suggested thinking about or hearing how somebody answers a question. The other thing, if you go here for scoring rubrics, we've got the answers to each of those things. But right there, that link is the link to the scoring guidelines again, but also it's got student samples. I know we did some of this in class, but people asked also to see, well, what did it look like when a student actually wrote this? And down here at the bottom of each one, it tells you how many points were earned and what did and didn't get the points. So this is going to be way, way, way too much for most of you to do. And that's somewhat the point, is to find the thing, the piece of this that you're most interested in. Maybe it's you're just going to read this page. You're going to stop this video right now and read over this page. Maybe you're going to listen to me talk through this page. Maybe you're going to watch some of the videos talking through some things. But a few things I want to emphasize before losing people here is, if you're on this link right here, it takes you to what they call the keyboard and tip sheet for the AP Chem exam. So there's a few things here that might help us to know what to expect. They still could have you use symbols, so we still might say delta H. They still might have you write a rate law or a K expression to using exponents or divisions or subscripts. We've got all of those things. They're not worried about subscripts and charges. Even sulfate, which has a subscript and a superscript, we can type that in easily without wasting our time. We can write reactions without worrying about exactly what the arrows should be or shouldn't be. We can write a net ionic still. So that's on sample on one of these. But down here, this was an interesting thing. They did show how you could type out some mathematical work. So I don't know that we're going to be doing any calculations. I also don't know that we won't. So if whether you're thinking about typing or not, this sheet kind of gives us an idea of what things are they saying won't necessarily be eliminated. So that's all there for us, and hopefully a little bit helpful and saying what could or couldn't be there. The other thing that I want to point out is, if you go to the AP course schedule, the coronavirus updates there, when you go down to AP Chem is every day at 10 a.m. Obviously, we've got a lot of old ones here. It says they're 45 minutes. You can see some are 45, some are shorter, some end up a little longer. I've watched parts of a few of these, that, as you can see. But what may be super helpful is the one from yesterday. So Monday, well, who knows when you're watching this, from Monday the 4th, the answers to that from today, if you're watching this today, so maybe even going on right now, but where they're giving this timed practice. I'm going to watch those. I'm going to let you know how good, bad, or other I think that they are. But I did want to point them out right here in case you can miss my other communications. Maybe something will come out there, and I'll re-record this video even. But I wanted to start putting these videos together so you could have those. So back right here, just my overview. So we've got cheat sheets for each topic. If we were preparing for the normal AP test, we'd still think about each topic in cheat sheets. But with Stoic, it said we could do some math, but some highlights or some key things that they've been asking or expecting us to be able to explain. And we did this on one of our mock exams, is not just rounding to the number of significant figures, but making sure that we know that in a data table, the number of digits is important, and that with the tools we're using, that's what determines the significant figures. So if you're given something where you're reading a burette or graduated cylinder, make sure that you're estimating that one digit, which two lines is it in between. You might have to do a calculation, or you might have to do, like I've asked a few times, explain, well, what steps are you going to be going through using molar mass, mole ratios, using the ideal gas law, all of those things. So you treat it like you're doing it, you write it out. And it's always important to make sure that we know what these things mean. So like limiting the thing that runs out and determines how much we can make, the thing that is left over, how much we made compared to what we should have made calculation wise. So just kind of refreshing those things in your head that you're just so used to doing with math. With reactions, it definitely is possible to have net ionics. Make sure that you could either write it or explain the idea very specifically and relevant to the equation that you're given. Don't just talk in generalities. Oh, we have ions and solids. Say sodium plus is a spectator ion, or PbI2 is the solid that's formed. When we're talking about strong or weak things, whether they're totally or partially ionized, and if we write a net ionic, we remember that strong acids and strong bases are written separately. Know that the conductivity is based upon the movement of charge, and specifically the movement of ions if we're talking about a solution. Beer's law is our connection between absorbance and concentrations. We make calorimetry or calibration curves. We do colorimetry. That's where we are using a colorimeter and we're measuring how intense the color is. And with oxidation reduction, we could justify is something redox or not by knowing our oxidation numbers. With thermo, remember that it's focusing on enthalpy. So there's a lot less or very little or likely no entropy and no free energy. So the difference between endo or exothermic in terms of temperature, in terms of H, in terms of the heat flow from system to surrounding, in terms of the graphs, which it says down here. I've bolded a few things throughout this because I think that those are things that we've seen enough before from the College Board that they could come back again. So a calorimetry experiment where we're measuring temperature changes, because you could be asked about specific heat, about temperature changes, about heat flow, about system surroundings, about the mass of it, how all of those impact it. That's a good way to connect data to this, maybe then go down some road with bonding. Remember bond energy, we're thinking about broken minus formed, which is reactants minus products. And the potential energy graphs, those are the big uphill or downhill, where it also connects with activation energy, the total bonds of reactants, the total bonds of the products. Equilibrium is something that's sometimes hard to imagine it being non-calculation based. We could still write a K just like it showed on the equation sheet there. We could still maybe even do a calculation with the K, but probably a lot less just pounding out some math there. So graphs, the idea that we're graphing either concentration rate versus time. At what point do we get to equilibrium? As we look at the increase, decrease, or constant nature of the graph, what does that mean at different times? What are some things that make reactions not lead to equilibrium? When we have gas, when it's escaping, when we have an open system and something's leaving. When two ions form a precipitate, that does form a solubility equilibrium, but in terms of a one-way reaction, it tends to just go that one way. We can do K as products over reactants, but we can also think of just, is it a big or a small K, meaning it goes very far to completion or it doesn't. And here I bolded the reminder that no matter if I add or remove something, change pressure, change volume, the K value stays the same. Only heating it up or cooling it down changes K. I think Le Chatelier's principle and the idea of, okay, we do this stress, we change the temperature, we change the volume, we do whatever, explain what happens and why. And you're always thinking that it's because we're trying to get back to the ratio from before. I added more, I have to use that up to get back to where I was. I put something else extra in, I have to use it up. I take something out, I have to make more of it. All of those things. And do remember that solubility, precipitates, all of that does have to do with equilibrium as well. One important thing there is that a common ion, that's a salt water, sodium chloride, in the water, and I added, and I had something like silver chloride. Well, the extra chloride impacts the silver chloride precipitate. Atomic is a very important one in terms of explanations. I didn't put it as one of our assigned ones, but more of an optional one, but it might be worth going back to look at, because being able to explain two differences here, whether it's any of these trends, you're definitely focusing on right here. I should bold that, I will. The ZEF is how much positive charge we have attracting it. The shielding is how much distance there are, and that's the connection to what is making my attraction large or small. Sometimes there's some exceptions that comes from electron repulsions, and we talk about attractions and repulsions without using the word one. And I did do a quick PES overall thing, and just making sure that you can read those graphs is important. Bonding is something that we did a lot of Lewis structure drawings. You won't have to do a drawing, but that we could be given a drawing or just given some things to ask about what this looks like. So ionic is important. It comes from Coulomb's law as well. So even though that wasn't bold, I'm going to bold just that word. It's how big is our charge? How big is or how far apart are our dipoles? You could be asked about shape or angles. With that, I would say definitely think about, they're not just going to ask only what's the bond angle and move on. That's too easy to just look up. That's too easy to cheat, to share, to find, to Google, whatever. They're going to ask, why does this happen? And it's all about how many electron regions are around the atom. And the more places you have electrons, the more repelling, the more it pushes everything together. When we're talking about resonance, or there's two different drawings, it's because those are both equivalent. And remember that the resonance is saying that it's really an in between those two things version. Formal charge sometimes is useful or is used to describe why one picture or Lewis structure might be better than another. You'd be given both of them. So you think about, well, how many electrons did it bring? How many electrons does it have around it? That gives us formal charge. We want that formal charge to be close to zero. The thing along with maybe all of these, and this is not just bold, you see it's all capped also, but the idea of what makes a molecule polar or non-polar, using phrases symmetrical, asymmetrical, and dipoles either canceling or not. When we get into gases, talking about the movement of the particles with the KMT. If we're describing pressure, we're using the word collisions. If we're describing temperature, we're talking about particle speed. You could be given a graph and thinking about what that tells us about temperature. You could be thinking diffusion and fusion, or other ways that we know about how fast the particles are moving when we connect with mass. The other thing in IMFs, I could make this way bigger, but I'm going to mess with my formatting here, is that IMFs you will have to explain. I think that there's no doubt there. So know the main types of IMFs. Know that everything has LDAs and be ready to use and understand the phrase polarizability. My all caps here was when we're describing which ones are stronger, yes, we compare LDFs to hydrogen bonds, but it's really the data that proves that in this case, this is the strongest melting point, boiling point, pressure, state, solubility, all of those things. With solubility, you're talking about the attractions you have and you break. And that's where we start to get into induced dipoles. And then with different types of solids, just the reminder that several solids, ionic, metallic, and network solids, are all held together by bonds, which are much, much stronger than IMFs. We just racked up kinetics, so hopefully that's a little bit fresher in your mind. But probably a great thing to be able to explain is the factors, the collision theory, why the particles can move and how they can move. But obviously, we saw in the equation thing, we could still do a rate law. We could get that from graphs. We could still write equations and think about mechanisms or catalysts, making sure we know the right word for that. So these are what I think, after looking back through these topics, maybe the most likely things you would have to explain, with some key words, phrases, or thoughts that go along with them. With this, like printing this page out and just seeing, oh, calorimetry experiments, factors, that's not a helpful cheat sheet. You would be thinking, okay, do I on a thermo cheat sheet have some stuff about calorimetry, or do I go back to the thermo video? If I didn't go back to the thermo video, or it wasn't complete enough for me. We've got energy diagrams. Oh, sorry, that's the thinking the wrong way there. Where is, that's near the end. Sorry, I don't know what order they did everything, but there, enthalpy. So section 6, heat capacity, Hess's law, all of those things, energy diagrams. Remember that 9 and 8, which they did cover on here, are not going to, going to be tested, but anything 1 through 7. So that's just my guess. It's just putting my thoughts together another time. So as you go through this, remember that you can just do the question, click on the answers. You could do the question, listen to my or watch my quick video going through the question. You could do the question, go to the answers, and then also go to student samples. I'm not expecting you or wanting you to do all of that. I want you to find a balance, and maybe cutting this off right now, or maybe you cut it off a long time ago, is what you need. Maybe just shutting this whole thing down and focusing on those few AP videos is what you need. But we're getting really close. You guys know so much. We've done so much review. We're going to hit one more thing, which is just a quick review back through the labs. But that's about it in terms of making sure that we do stuff other than just getting good practice and feeling ready. So that was my kind of overview of explanations with my potential topics here. Yeah, thanks.